All right, crew. So I want to start off actually going back to the worksheet that you guys were working on Tuesday in class. And in particular, I want you to focus in on question 2A because I suck and I was wrong with the answer that I was giving to some people. And I just want to make sure that everybody is on the same page when it comes to looking at these two structures. So if you recall, I asked you to figure out what the structural formula was for each of these two things. So let's quickly throw this together, and I'll show you what they look like, and then we'll talk about the different intermolecular forces that exist, and then you'll be able to determine which one has the greater intermolecular force. Okay, so you can see with this first one here, I think Smadden was the first one to show me this, and I told him he was wrong when in fact he was totally right in creating this structural formula, this Lewis dot structure here. And the important thing to understand here is that it's a trigonal pyramidal, not a trigonal planar as I originally forced you guys to think it was. So it's trigonal pyramidal. And however, in this case, while it certainly is polar because the fluorine is going to have a higher electronegativity than the phosphorus, so that means we're going to have the bottom part of this, let me just use red here, this is going to be the negative side of the molecule, and this will be the more positive side of the molecule. So we have one of these permanent dipoles that will exist. So if it is dipole, then the next question is it a great enough difference in electronegativity to warrant it being a hydrogen bond? And in this case, it is not. So you're simply going to have dipole-dipole forces here. Now, of course, if you have dipole-dipole, you also have the next weaker of the intermolecular forces, and that means dispersion forces as well. But keep in mind that dipole-dipole is going to trump those dispersion forces. So let's take a look then at what's going on with our PF6. Now, as you know, there are some exceptions to the octet rule, and this is one such case. And because you can see here that instead of having 8 electrons, the central phosphorus there actually is going to have 10 electrons that it shares. So that seems a little bit wacky. Now, the important thing for us to think about here, though, is what is the molecular geometry associated with this? So for that, let me import an image that shows it more clearly because it'll be in 3 dimensions as to what's going on. You may look at this and think that it's sort of like a flat hexagon, when in fact it's not. It's a 3-dimensional structure. In fact, I think it's an octagon. Hold on. Okay, so what we have here is sort of a quasi-space-filling ball and stick model. And if I were to sort of label these things, each of these white balls would be the fluorines. So you can see that we have a flat plane that exists there, and then a triangular plane here, another one here, here, and I'm not going to draw all the other ones, but this does make an octahedral shape that would exist here. But most importantly, while there certainly would be a difference in electronegativity that would still exist between the central phosphorus, and so I'll just put the P right here, and the surrounding fluorines, because they're all pulling in the exact same direction all together at the same time, there is not going to be any dipole that will exist across the entirety of this molecule. So in this case, there's no dipole, so that means the only thing we have are dispersion forces. And if we have dispersion forces here, and that's the only thing that's in play, and over here we had dipole-dipole, if you were to judge as to which one is going to have the stronger intermolecular forces, obviously you would say that the PF3 is going to have the stronger intermolecular forces because it has dipole-dipole as opposed to the weaker dispersion. Now, let's take it a step further and talk about what it is that I want to discuss today, which is imagine that you had both of these compounds in a beaker and you were trying to boil them. Which one of these two is going to have a higher boiling point? In other words, which one is going to require more an input of more heat energy and therefore boil at a higher temperature? And I hope you would understand that it would actually be this dude right here, because the intermolecular connections that exist among all those PF3 molecules is stronger, and therefore you'd need to have more heat energy to overcome those intermolecular forces, the dipole-dipole forces.